Hi everyone, this is Professor M. Science, and today I want to discuss the power series solution to the 3D isotropic quantum harmonic oscillator in another one of our videos on rigorous quantum mechanics. Now, if you've been following us for a while, you're probably thinking that we've already solved this problem in another one of our videos. In that video, we write the 3D oscillator as a tensor product over three 1D oscillators. And once we've done that, the solution is pretty straightforward. So you're probably wondering, why on earth would we want to solve this again? Well, today we're going to study the 3D harmonic oscillator from a completely different angle. We're going to treat it as a central potential. Now, this will serve two purposes. First, it is actually generally a good idea to try and find different solutions to the same problem because they might give us new insights. In this context, treating the 3D oscillator as a central potential will allow us to introduce angular momentum into our discussion. And secondly, it turns out that the mathematical solution of the 3D oscillator when treated as a central potential is really similar to the solution of the hydrogen atom. Because the harmonic oscillator is a problem that we know so well, if we tackle it first, it'll give us the confidence that we will need to then solve the harder problem of the hydrogen atom. Today, we're going to focus on the mathematical solution of the problem. But there is also a companion video where we will take the mathematical solution that we're going to derive today, and we explore the first few energy eigenvalues and eigenfunctions. So I really encourage you to check out that video as well. So let's go. Let's think about the three-dimensional isotropic quantum harmonic oscillator. Working in the position representation and using Cartesian coordinates, the Hamiltonian H has a kinetic energy term, and then the defining feature of a harmonic oscillator is the quadratic form of the potential energy term, which in 3 dimensions can be separated into a term proportional to x squared, a term proportional to y squared, and a term proportional to z squared. If we now insist that we have an isotropic oscillator, this means that the frequencies are the same along every Cartesian direction, and we are simply going to call them omega. We can then rewrite the Hamiltonian with the same kinetic energy, and for the potential energy, we can take this common factor multiplied by this sum of squares, and with this we can see that the potential no longer depends on the individual x, y, and z, but only on the sum of the squares. Using spherical coordinates, this is simply the square of the distance r from the origin, and this means that we can rewrite the Hamiltonian of a three-dimensional isotropic oscillator in spherical coordinates with the usual kinetic energy term, and a potential energy term that is equal to 1/2 m omega squared r squared. And this here is the key to today's video. The three-dimensional isotropic quantum harmonic oscillator is described by a central potential. For completeness, we can also write down the Hamiltonian H by spelling out the kinetic energy term in spherical coordinates, and as discussed in the video on central potentials, it is given by this prefactor multiplied by a term that involves the derivative of r, and then a long term that involves the derivatives of the angular variables. And finally, don't forget the potential energy term. We're now ready for this video. What we will do today is to use our knowledge about central potentials to solve the eigenvalue equation of this Hamiltonian. And if you need a refresher about central potentials, you can find every single relevant link in the description. As we've just discussed, the three-dimensional isotropic oscillator is an example of a central potential. Using this Hamiltonian, we can build its eigenvalue equation like this, where as usual, these are the eigenvalues and these are the eigenfunctions. And our objective today is to solve this eigenvalue equation. In the videos on central potentials, we learned that the Hamiltonian describing a central potential commutes with the orbital angular momentum operators. What does that mean? It means that the eigenfunctions of the Hamiltonian can be chosen to also be eigenfunctions of the squared orbital angular momentum and eigenfunctions of the z component of orbital angular momentum. Now, you'll remember from our series on angular momentum that in the L squared eigenvalue here, small l can only take non-negative integer values. And that for the Lz eigenvalue here, for a given small l, ml can only take one of these values. And if you need a refresher about orbital angular momentum, you can also find all the relevant videos in the description. Another important result from the videos on central potentials is that the common eigenfunctions can be labelled by the three quantum numbers k, l, and ml like this. Now, L and ml are the quantum numbers associated with orbital angular momentum, and k gives us the energy spectrum for a given L and ml. We can also find that the energy eigenvalues can be labelled with k and l, but that they don't actually depend on the ml quantum number. The next key insight that we learned in the videos on central potentials is that these three equations imply that we can write the common eigenfunction psi as a product of a function r that only depends on the radial coordinate, and another function y that only depends on the angular coordinates. These functions y are called the spherical harmonics and are labelled by the angular momentum quantum numbers L and ml. We have a full video on these spherical harmonics, and as always, you can find the link in the description. The important result for us today is that the spherical harmonics are the same for any central potential, which means that we already have the solution of the angular part of the eigenfunctions of the isotropic harmonic oscillator before we even start. It is given by the spherical harmonics. This part here is called the radial part of the eigenfunction, and it depends on the quantum numbers k and l. But we found in the videos on central potentials that it doesn't depend on ml. This radial part is the most interesting part, because its form depends on the specific central potential that we have. And so the aim of today's video is to determine this radial function for the specific case of an isotropic harmonic oscillator. Now, a quick important note before we delve into the solution. Today's focus is on the maths, which is, I'm not going to lie to you, a bit lengthy, but it provides a nice example of what is involved in solving eigenvalue equations of central potentials, which is going to be really good practice for looking at more interesting problems such as the hydrogen atom. And of course, once we've solved the maths, we can then explore the physics. We have a companion video where we take today's mathematical solution and explore in detail a few examples of the energy eigenvalues and eigenfunctions of the three-dimensional isotropic oscillator. I really encourage you to also check it out, and the link, as always, is in the description. So, all we really have left to do is to determine the radial part of the eigenfunctions. As we learn in the videos on central potentials, the radial function obeys the so-called radial equation, and we have a full video discussing some general features of this radial equation. Just as a quick reminder, what we learn in that video is that the radial equation is given by a kinetic energy-like term in the coordinate r, a term that depends on the L quantum number, and the central potential itself, all acting on the radial function, and equal to the energy eigenvalue multiplying the radial function. Both energy eigenvalues here and radial functions here only depend on the k and l quantum numbers. This is the first step of our solution. As we already know the angular dependence of psi, we can reduce the full eigenvalue equation for psi into this new differential equation that will allow us to determine the radial part. So we're all set. In the rest of this video, we will simply solve this differential equation. The first step is one we already discussed in the video on the radial equation of central potentials. It is convenient to make a change of variables and set the radial function as equal to 1 over r times a new function u. With this new definition, we can rewrite the radial equation as given by this long differential operator acting on the u function and equal to the eigenvalue times the u function. So what have we really accomplished? This new equation for u is simpler than the original one for r, because this differential operator has a simpler form. There is, though, an extra point. To ensure that we get physically valid solutions, we also have a boundary condition on the u function, which, when evaluated at the origin, must vanish. Now, everything we've discussed so far is true for any central potential, and for the full derivation, I once again refer you to the corresponding videos that are linked in the description. The new thing that we will do today is to actually solve this differential equation for the isotropic harmonic oscillator. Solving this equation will allow us to determine the u function, and then we can use it to build the radial part of the energy eigenfunctions from this relation up here. We are going to tackle this differential equation postulating a power series solution, a general strategy that is also used to solve other problems such as the hydrogen atom. But before we postulate the power series, we're going to try and simplify the form of the u function further by considering a particular limit. That limit is the limit of r going to infinity. In this limit, we have that this term, proportional to r squared, dominates over this other term that has r in the denominator, and over this term that is a constant. As such, we can approximate the full differential equation as containing the derivative term and the quadratic term, all acting on the function u and all equal to 0. In this limit, the dominant terms of the solution are this positive exponential and this negative exponential. And you can check this by plugging them into the differential equation, and you'll find that the derivative leads to a term proportional to r squared times the exponentials, and another term proportional to the exponentials. In the limit of large R, this second term can be neglected. Moving on, these two solutions are clearly not the full solution because we are neglecting two terms in the differential equation. However, this is what we expect the solutions to look like in the limit of large R. Now, note that of the two solutions, only the negative exponential is in fact a physically acceptable solution. And this is because the other solution diverges for large R and would lead to solutions that cannot be normalized. So why did we bother with this limit in the first place? What we're going to do next is to go back to the full range of allowed values of R. And inspired by this limit behavior that we've identified, we will write the true u function as equal to this exponential times a new function that we're going to call v. So what do we accomplish with this change? As we know what the solution must look like in the limit of large R, by singling it out, we are hoping that this will lead to simpler maths. But before we go on, note that by singling out the negative exponential, we haven't actually removed the unphysical positive exponential solution, so we're still going to have to deal with that later on. Let's now see what the differential equation becomes with this latest change. Remember that we are rewriting the function u as equal to this exponential times this new function v. The tricky term is the derivative here, so let's write the second derivative of the new expression in terms of v. We can now use the chain rule to expand the derivative as the term involving the second derivative of the exponential, plus the cross term, which is 2 times the first derivative of the first term, times the first derivative of the second term, plus the term involving the second derivative of v. We can now consider this term, which is the first derivative of the exponential, and we can easily evaluate it. From it, we can also evaluate the second derivative of the exponential. Plugging in this expression for the first derivative, we then again use the chain rule, getting this term plus this term. Putting everything together in this second derivative, we start with an exponential common factor, then considering this first term up here, we get a term proportional to the function v. From this middle term up here, we get a term proportional to the first derivative of v. And from this final term up here, we get a term proportional to the second derivative of v. Let's make some room. And let's copy the latest expression we got for this second derivative. We can now insert this expression we got for the derivative inside the differential equation all the way up here. And we end up with the common exponential factor. We can copy the long derivative term we just derived. And then we have the L-dependent term, the central potential term for the isotropic oscillator, and we are now moving the energy eigenvalue to this side of the equation, all acting on V and all equal to 0. We can take a final step to further simplify the form of this equation. First, we can remove the common exponential factor as we are equating to 0. Also, these two terms combine to 1/2 h bar omega, and these two terms combine to minus 1/2 m omega squared r squared. We can then cancel this term with this central potential term. And overall, we end up with a term proportional to the second derivative of v, a term proportional to the first derivative of v, and a term proportional to v, all equal to 0. In this last step, all we've done is to rearrange the expression above, but feel free to pause here for a moment to make sure that you really are happy with all of this. So, this is the latest differential equation that we've derived, and solving it will give us the function v. But before we do that, remember that we had a boundary condition for the function u such that it vanishes at the origin. Remembering the relationship between the u and v functions, we can straight away conclude that we get an analogous boundary condition for v. This is a good moment to recap. Solving this equation will allow us to determine v. Once we've got v, we will be able to calculate u using this relation between the two. And once we've got u, we will be able to get the original radial function r using this relation between the two. Finally, once we've got the radial function, we will be able to build the full eigenfunction psi, and this will be accomplished by multiplying r with the corresponding spherical harmonics. Now, I realize that this may look like a rather convoluted path to determine the eigenfunctions, but at the end of the day, we started with a really complex differential equation, so we never expected the solution to be straightforward. But we're now ready for the final push. All we have left to do is to find out what v is. And as we anticipated a few minutes ago, we are going to write v as a power series. We set it equal to r to the power s, and then a power series in r. We can also rewrite it by taking the r to the power s inside the sum. And note that we're starting the power series at q equals 0. What this means is that by definition, we choose c0 to the lowest non-zero coefficient. Or to put it another way, as we insist that the q0 term in this sum is non-zero, then the lowest power in the expansion is this s here. Of course, this choice will not affect the final answer, it's just a convenient way for us to write the power series. Looking at the differential equation at the top, we see that the tricky terms will be the derivatives. If we start with the first derivative of v, we can write it as the derivative of the power series. And we can very easily calculate the derivative of each power in the sum to get this new sum. Now similarly, we can consider the second derivative of v, and this is equal to the first derivative of this expression that we've just derived. And we can again easily evaluate the derivatives of the powers to get this other sum. We're now ready to rewrite the full differential equation at the top in terms of the power series. Every term will feature the summation over the c coefficients, so we can start with that. We then have the first term at the top here, which involves the free factor, and then the second derivative of the power series that we've just derived. And note that the power is q plus s minus 2. Moving to the second term at the top here, we have this prefactor, and then the first derivative of the power series. Note that the power is now q plus s, which we get by combining the q plus s minus 1 power here with the r factor all the way over here. Moving on, we have the third term here, which gives this long prefactor, times the power series, and finally all of this equals 0. So, starting with the differential equation for v at the top here, we have then expanded v as a power series as shown here, and this is the latest expression that we got for the differential equation when using the expansion of v. To simplify this further, we can combine this factor of r squared in the denominator here with this power over here to get a power of q plus s minus 2. We can then rewrite the whole expression starting with the sum over CQ, then grouping together the q plus s minus 2 powers, and then the q plus s powers, and all is still equal to 0. Feel free to pause here again to double check this last step, but all we've literally done is to rearrange the terms. The next thing we need is to look at the boundary condition at the top here. We can now rewrite this condition expressing v as a power series, which when evaluated at the origin must vanish. For this equation to hold, we must have that s must be strictly larger than 0, otherwise we would have a constant non-zero term in the sum that wouldn't vanish at the origin. So, putting everything together, we have that the power series expansion coefficients must obey this equation at the top, and that the boundary condition means that s must be positive. Whenever we have a power series equals 0, then we must have that the coefficients in front of every single power exactly vanish. Now, inconveniently, in the expression we have here, every term contains two different powers, q plus s minus 2 here, and q plus s here. And this means that we need to be extra careful when setting the coefficients of each power to 0. To explore what is going on, let's look at the first few powers explicitly, and to simplify notation for now, we will call this first term AQ and this second term BQ. Let's start with the lowest power in the series, which is s minus 2. The term proportional to the a coefficient here gives a power of s minus 2 when q equals 0, which means that we end up with this term proportional to c0. For the term proportional to the b coefficient here, the lowest power in this term is s, so it does not contribute to this term, which has a power of s minus 2. As every power in the top equation must vanish, then these coefficients of the first term must be equal to 0. The next power is s minus 1. The a term gives a power of s minus 1 when q is equal to 1, and we have this term proportional to c1, and again the b term doesn't contribute. We finally require that this coefficient of the r to the power s minus 1 vanishes. The next power is s. The a term gives a power of s when q is equal to 2, and we have this term proportional to c2. And now the b term does contribute with its lowest power, which corresponds to the q equals 0 term, so we end up with a term proportional to c0. Again, to obey the top equation, the coefficients of rs must vanish. And we could go on like this term by term. And the general power q plus s has contributions from the a term proportional to cq plus 2 and from the b term proportional to cq. And again, these coefficients must vanish. What does this all mean? In order to determine the form of the v function, we need to determine the value of all the expansion coefficients, and these equations here will allow us to do so. Let's start with the first one, corresponding to the power s minus 2. So, this is the first equation that the expansion coefficients must obey. Using this expression up here for AQ, we can write down A0 explicitly by setting Q equal to 0. And we get the prefactor multiplying the first term plus the second term. We can now insert this expression for A0 into the equation up here and end up with C0, multiplying the expression we just got for A0 and all equal to 0. And remember that by definition, C0 is the first non-zero coefficient, which means that this bracket must vanish to obey this equation. In principle, there are two possible solutions. Either s is equal to minus L, or s is equal to L plus 1. However, remember that the boundary condition that forces the function v to vanish at the origin implies that s must be strictly larger than 0. And remembering also that the quantum number L is non-negative, then these two results together mean that this solution up here is not possible. And in turn, this means that the only valid solution is s equals L plus 1. And this result fixes s. Okay, so going back to our set of equations, we see that the next one corresponds to the power s minus 1. Using the general expression for AQ up here, we can write down A1 explicitly. The equation for C1 here then becomes this. In the discussion of the vanishing of the previous power, we established that s equals L plus 1, and this implies that this term in brackets here is not equal to 0. It then follows that this equation will only be true if C1 is 0. And overall, this means that there is no C1 coefficient in the power series of V. Now going back to our set of equations, we're now ready to look at the general power Q plus S. Using this equation here, we can insert the expressions we have for A and B to get CQ plus 2, then the expression for AQ plus 2, plus CQ, plus the expression for BQ, all equal to 0. From the lowest power equation, we know that S equals L plus 1, and using this expression for S in the various instances here, here, and here, we end up with this new term proportional to the CQ plus 2 coefficient, and with this new term proportional to the CQ coefficient. In this step, I have made some trivial rearrangement of terms, so feel free to pause here to cross-check this substitution. Overall, we've ended up with a recurrence relation between CQ plus 2 and CQ. And we can rearrange the terms and write it in this more conventional form, with CQ plus 2 over CQ equal to this long numerator over this long denominator. Let's recap. We are seeking a solution to this differential equation up here, subject to this boundary condition. We have started by postulating a solution in the form of a power series that we write like this. And we've now established that the expansion coefficients in this power series must obey this recurrence relation between CQ plus 2 and CQ, and we also have that Z0 is different from 0 by definition, while we found that C1 vanishes. With this information, we're now ready to understand the form that the power series takes. As C1 is 0, and the recurrence relation relates expansion coefficient CQ with CQ plus 2, then we can conclude that CQ will vanish for all odd Q. As C0 is non-zero, In general, we will have non-zero coefficients with even q, and we'll be able to write all of them as proportional to C0. This means that we will be able to write the full power series in terms of the C0 expansion coefficient. And finally, we will be able to fix C0 itself by normalizing the resulting wave function. The next question we explore is whether the series is finite or infinite. Mathematically, we can have both options, but we'll see in a moment that for normalizable solutions, we can only have a finite series. Let's first suppose that we have an infinite series. To be clear, remember that we are considering the series expansion of the v function like this. In this case, we can take the limit of large Q for the ratio of CQ plus 2 over CQ. And using this expression up here, we get this prefactor. The dominant term in the numerator is h bar omega q, and the dominant term in the denominator is q squared. Simplifying, we end up with 2m omega over h bar multiplying 1 over q. This means that if we have an infinite series, then for very large q, the ratio of consecutive coefficients tends to this value. Let's keep this in our mind, and we will come back to it in a moment, but first we need to consider an extra ingredient. To understand what the limit we just discussed means, we will now show that it is the same limit as that of a rather simple function that we can easily analyze. Let's consider the power series expansion of this exponential. We can write the exponential as this sum over p of the usual power expansion for an exponential. And for convenience, we're going to rewrite it as the sum over p of an expansion coefficient a to p times the power, where a to p is simply the original expansion coefficient. We can now calculate the ratio a to p plus 2 over a to p. Plugging in this definition, we get this for the numerator and this for the denominator. The 2 factorial terms simplify to 1 over p plus 1, and the 2 powers simplify to m omega over h bar. You can now probably see where we're going. If we set q equal to 2p, then we can rewrite the ratio as aq plus 2 over aq, which is equal to this fraction involving q and this factor. Taking the limit of large q, we end up with 2m omega over h bar, multiplying 1 over q. So let's now go back to our series expansion for the function v. We've just established that if we consider this exponential as a power series, then the limit of large q for the ratio of consecutive expansion coefficients is equal to this expression. Now these two expansions are slightly different because of this power of s here in this first expansion, which is not present in the expansion of the exponential. However, we can think of it as simply providing a rigid shift in the comparison of the expansion coefficients between the two series, which becomes irrelevant in the limit that q tends to infinity. Overall, this means that both limits for large q are the same. And in turn, this means that if our series expansion for v is infinite, then the v function behaves like this exponential for higher order terms in the expansion. But this is a problem because this exponential has a positive argument, so it diverges for large r. This means that v is a physically unacceptable solution because the resulting wave function would not be normalizable. Now, how can we avoid this unphysical solution for v? Well, physically relevant solutions are such that the power series must have a finite number of terms, so we must have a finite series. We'll explore what that implies in a moment, but first a quick aside. Having an infinite series, which is a mathematically valid solution, leads to the physically invalid solution we already found when we solved the differential equation in the limit of large r, but now appearing for the full equation. So, how can we make this power series finite? there must exist some value k such that CQ is equal to 0 for all q larger than k. Looking at the recurrence relation up here, we see that the CQ plus 2 expansion coefficient will be 0 if the numerator here is equal to 0. So the series will terminate at CK if the numerator of the recurrence relation vanishes, which means that h bar omega times k plus L plus 1 half h bar omega minus EKL equals 0. Rearranging, we get that the energy is equal to h bar omega times k plus L plus 3 halves. And remember that the label k here can only take non-negative even integer values, while the label L here can only take non-negative integer values. So, by insisting that the series must be finite, we have now come to a key result. The energy of the 3D isotropic quantum harmonic oscillator is quantized, and the energy levels are given by this expression. An important feature of these eigenvalues is that they are highly degenerate, and we explore more about this in the companion video, so don't forget to check it out. Okay, that's it. After this, admittedly very long, mathematical derivation, we now have all the ingredients that we need to study the energy eigenvalues here and eigenfunctions here of the 3D isotropic quantum harmonic oscillator Hamiltonian, written as essential potential here. We will finish with a brief summary of the key results, which we then use as a starting point in the companion video to explore a few examples of the eigenvalues and eigenfunctions, so don't miss that video. The full eigenfunction psi is given by the product of a radial part and an angular part. This angular part here is the same for any central potential and is given by the spherical harmonics. The radial part here depends on the precise form of the radial potential. What we've done today is to solve a complex differential equation to determine this radial part, and to do so we've taken a rather large number of steps. First, we've rewritten the radial function in terms of a new function u like this. Then, by considering the limit of large R, we've defined yet another function v, which is related to the u function via this expression. Next, we've written the function v in a power series like this, in terms of expansion coefficients c. And the lowest power s in the expansion is equal to L plus 1. Finally, we've shown that the expansion coefficients obey a recurrence relation between CQ plus 2 and CQ, which is equal to this prefactor multiplied by this long numerator over this long denominator. We also have that the first non-zero expansion coefficient is C0, while C1 is equal to 0. This means that all odd expansion coefficients vanish, and that all even expansion coefficients can be written in terms of C0. We can then complete the solution by fixing C0 through normalizing the wave function. And this is it. This is all we need to determine the eigenfunctions. Once we've determined what these C expansion coefficients are, we can construct V. Once we have V, we can construct U. Once we have u, we can construct the radial function, and once we have r, we can finally build the eigenfunctions. With this recipe, we can build any eigenfunction we want, and we look at a few examples of how to do this explicitly in the companion video. Well, I hope you've liked the maths. So what next? I really encourage you to check out the companion video where we explore the first few energy eigenvalues and eigenfunctions of the 3D isotropic oscillator. And you should also check out our series of videos on the hydrogen atom, where we use a very similar strategy to solve the eigenvalue equation. And as always, if you liked the video, please subscribe.